So what if we now make our system a little bit more complex? Say that it's like in the olden days and there's a wedge in the middle of the seesaw. It's been put there so that people can push it when they're standing up. So imagine that a person comes along and pushes this seesaw, say with the 1 Newton force here at a distance 1 unit from the fulcrum. Okay, you can see it's going to make the seesaw tip in the anti-clockwise or the positive direction. So let's see if you can write down now on your notebook that use this diagram of the seesaw and write down all of the forces and then what's happening when there's a 1 Newton force being applied there. So what is happening if someone comes along and applies a 1 Newton force in this direction? Well, we have our original forces at 4 units from the centre on this side. We're saying it's 4 metres. We have a 2 Newton force and we have a 0.5 Newton force. And that's the line of action and that's the moment arm. Here now we have a 1 Newton force at a distance of 1 from the pivot point. And back over here on this side we still have, at 5 units, we still have a 2 Newton force along its line of action, and its perpendicular arm back to the centre is 5. So how do we write that? So here the moment due to this force is force times perpendicular distance. The total force is 2 plus 0.5 newtons times the perpendicular distance, which is the perpendicular line from the line of action back to the pivot point, which is 4. So the total moment here is 10 Newton meters. Same over here. We know force times perpendicular distance. The moment is that, and it's 5 times 2, which is 10 Newton meters. So, and we know that this is in the positive direction because it's going that way, counterclockwise. This one over here is in the negative direction as before. And now we're adding this one. Well, first of all, it's a 1 Newton force. The weight is going through the pivot point, but the line of action, which is where we're pressing, is here. So, to work out the moment due to this force pressing on here, we have to take the moment is equal to the force, which is 1 Newton, times the perpendicular distance, which is also 1 metre, and so there's a moment of 1 Newton metre there. The line of action times its perpendicular distance. And that's the trick with moments, is working out where is the line of action of the force. So the total, and that is also in the counterclockwise, which is the positive direction. So that some of the moments here would be plus 10 from this one, plus 1 from this one, minus 10 from this one, all in Newton meters. So it adds up to 1 Newton meter. So that's an equation that describes what we saw, that when someone presses here, there is an overall moment in the counterclockwise or positive direction. Of course, if someone else came and pushed exactly in the opposite and equal direction at the same distance, it would make no difference and it wouldn't tip the ruler. Now what I'd like you to do is to spend some time moving your 20-cent pieces and 5-cent pieces up and down your ruler and writing the equations for what's happening when you move them there. For example, here we have, this is now at 4 units away and this is now at 3 units away, and it's balanced again. So what's happening there? Any system that looks like this, whether the beam is this way or horizontal, if everything is perpendicular forces and vertical and horizontals, it's very easy to work it out. It's just like a complicated seesaw system.